So now we will study to design a single angle compression member for a load subject to a corresponding length. So in this question we have to design a single angle discontinuous strut to carry a load of 50 kilonewton in working condition, and the length of the strut is 3 meter, and it is connected to a gusset plate of 12 mm thickness with a 20 mm diameter bolts. Design the connections also. So we have to assume the remaining factors, and we have to use IS 800 and IS 80 code, which is a steel table code, to solve this. And also we know that section 7 of IS 800, which is in page 34, gives the procedure to design the compression members. So here the gusset plates and angle section is made up of grade Fe410. We have to assume that, which means the ultimate strength of the member will be 410 newton per mm square, which is the Fu value, and the yield strength will be Fy, which is 250 newton per millimeter square. The bolt is given with a nominal diameter of 20, and we will assume it as a bearing type of bolt having grade 4.6, which means the ultimate strength of the bolt will be 400 newton per mm square. This can be used in our design of connections, that is the number of bolts. Now here the 50 kilonewton given is a working load. So working load is a load which is acting in a serviceable condition, but always we have to design the connection for the factored load. So the factored load will be 1.5 times the working load, which is 1.5 into 50, which is 75. Next we have to uh, calculate an effective sectional area, so that from that we can select an angle section. So here we will be using the factors like slenderness ratio for directly selecting the design compressive strength. So the details again regarding the design compressive strength is given in clause 7.1.2.1 in page number 34, and it is basically a stress value. That is, usually we know stress is load by area, and by calculating the stress from the IS code, we can directly find the area required, and we can select a suitable section. So it is selected based on the slenderness ratio, and actually the code gives us a table, which is the table 9, which is given in IS 800 page number 40 to 44, where we can directly select a design compressive strength, which is the FCD value based on slenderness ratio and yield stress. So here the slenderness ratio need to be assumed, and we know that in table 3 of IS 800, which is in page number 20, the maximum value of slenderness ratio for a compression member is 180. So we can select a value below that. So I assume the value to be the slenderness ratio, which is KL by R, as 130. And we know that KL is the effective length, R is the radius of gyration. And usually minimum radius of gyration has to be considered. Now we go to the table 9C. Why? Because we know that all the angle section belongs to buckling class C, and this is obtained from table 10 of our IS 800, and this is in page number 44. And in page number 44, if you look down, and there is a heading called channel angle T and solid sections. In that, whatever may be the buckling axis, always the angle sections will belong to C class. So we will be referring 9C, the table which is corresponding to buckling class C. And if we cover the corresponding value of yield strength 250 and the slenderness ratio of 130, the design compressive strength is given as 74.3. Now we have to write that value. Now from this design compressive strength, we will find the effective sectional area required, and we will be designing based on that. And in clause 7.1.2, the design compressive load is given as effective area into the design compressive stress. Now from this effective area, AE will be the value of the design compressive strength divided by the design compressive stress value, which is FCD. And we know that the load factor load is the design load, and we will be selecting that as the PD value, which will be 75 into 10 raised to 3 divided by the design compressive strength. So load by stress will give you the total area required. So this is the area which we obtained, 1009.4. Now what we have to do, we have to go to IS 808 or our steel table and select an angle section having a cross section area greater than this value, this 1009.4. So when you go to the table steel table, I think in page number 8 there is an equal angle section, and here I select ISA, which is the Indian Standard Angle 90 by 90 by 6 mm. And when we look at it, is having a sectional area of 10.5 centimeter square, which will be equal to 1050 millimeter square. This value is greater than the required sectional area. And also we have to write the corresponding R minimum, that is a minimum radius of gyration, which is given as 1.75 centimeter and 17.5 millimeter, which will be equal to. So these values are obtained from IS80 table. So during design, always select an area greater than the effective sectional area required, so that our section will be safe. If we are selecting close to this value, then we have to redesign the section. Now we have selected the section, and based on the design compressive strength we assumed, now we have to design the connections. So here the question, it is given to design the connection, and the diameter of the bolt is given, so the bolted connection will be designed. The nominal diameter of the bolt is given as 20 mm. So the diameter of the bolt hole, which is D0, will be equal to 20 plus 2. The 2 mm will be the clearance for the bolt to pass, and this is obtained from table 19 in page 73 of our IS 800. Now what is the ultimate strength of the bolt? As we are using 4.6 grade bolt, ultimate strength will be 4 multiplied by 100, then we obtain 400 Newton per mm square. Also we can use table 1. I think table 1 has directly give the values of this ultimate strength based on the grade of bolt. Now the thickness value, which is used in the bearing capacity calculation. Now we know that the thickness has to be the minimum value of gusset plate and angle section. The angle section which we assumed was 90 by 90 by 6, and 6 mm denote the thickness, and gusset plate thickness which is given in the question is 12 mm. So in that calculation we have to use the minimum value, which is 6 mm. And also we are calculating the end distance and pitch distance prior, so that during the calculation of the bearing capacity of bolt, which will be easier. So the minimum end distance will always be denoted as E, and it is equal to 1.5 times the diameter of bolt hole. Now this is given in our clause 10.2.4.2 in page number 74. So you have to, while studying this problem, you have to use your code along with this, so that you can see what is written in each clause. So 1.5 into 22 will give you 33, and I assume it to be 35. Now the minimum pitch distance, or the distance between the fasteners, is also given in clause 10.2.2 in page 73, and it is given as 2.5 times the diameter of the fastener. Here our fastener basically means our bolt only, and that bolt means the nominal diameter is 20 mm, so it will be 2.5 times 20, and it will be 50 mm. So I am assuming the minimum value. Now for the design of bolted connection, as per clause 10.3.2 in section 10, and section 10 is the section which is dealing with the connections. Here it is written as the design strength of a bolt, which is VDB, is taken as the minimum values of the shear capacity, which is denoted as VDSB, and the bearing capacity, which is denoted as VDPB. Now we have to design the number of bolts based on the shear capacity and bearing capacity of bolts. All these are given in the codes itself. Now we go to clause 10.3.3 in page number 75 of IS 800. The shear capacity of a single bolt can be calculated. Now this is given by this equation of VDSB, and which will be equal to VNSB, which is the nominal shear capacity divided by the factor of safety for the bolt. Now the VNSB equation is also given under this clause, which will be FUB divided by root 3 into NN ANB plus NS ASB. Now what do you mean by NN and NS? As we know, the bolt will be having a nut, and this will be having a shank area, then there will be a thread area. So in the single angle section of a compression member, there will be only a single shear plane, okay, because there is a gusset plate, and gusset plate side we will be connecting an angle, and this will be having only a single shear plane. For the when this load is acting, that it will be sheared. Now either this bolt hole here, it will be either falling the thread area, or it will be falling the shank area. So NN denotes the number of shear planes, and NN means the number of shear planes passing through the thread area, and NS means number of shear planes passing the shank area. So what we do, that we assume the shear planes to be passing through the thread area. Now which means the NS will be 0, because NN is 1, So already the existing plane will be passing through thread area, so the plane which is remaining in shank area will be 0. So that is what is written here. Now what is the area of the thread area? So the area of the thread area means this is our diameter, which is 20 mm. So the area of the shank will be pi by 4 into 20 square. Now the thread area will be having much lesser area compared to sun. So we will be applying a 0.78 factor multiplied by the area will give you the area of the thread area, and this will be obtained as 245.04. Now we will be substituting all these values in the equation for the nominal shear capacity. FUB means it is the ultimate strength of the bolt. There is a small correction here IS code. It is written as FU, but actually you have to substitute FUB. So it will be 400 divided by root 3 multiplied by NN is 1 and NS is 0. So the whole term will become 0 and A and B is this value. And we will be getting a value of 56,589.56. Now we have to find the design shear capacity. So we have to divide by the factor of safety for the bolt. As we can see in table 5 in page 30 of IS 800, the gamma NB value for all the bearing types bolt is 1.25. So substituting this value, and we also will be dividing with 1000 or 10 raised to 3 to obtain the value in kilonewton. And I am getting the value of the design shear capacity of a single bolt as 45.27. Now we have to calculate the next capacity of the bolt, which is the bearing capacity of the bolt. Now the bearing capacity is given in the next clause, which is 10.3.4 in page 75, and the equation is given from the code is VDPP will be VNPP divided by gamma NP. N means nominal, and the VNPB's equation is given in this clause, which is 10.3.4 as 2.5 times KB, D, T and FU. Now KB is a constant which is based on these three parameters, and we have to take the least of E divided by 3D0, where E is the minimum end distance and D0 is the diameter of the bolt hole, and or it is P by 3D0 minus 0.25, where P is the pitch and D0 is the diameter of the bolt hole. FUB ultimate strength of the bolt, FU it is ultimate strength of the plate, or 1. And when we substitute all this value, because we have already calculated the value of end distance as 35, the value of diameter of bolt holes as 22, pitch as 50, we will be getting this value. In this, which is the least value here, 0.507. That will be used in our calculation of the nominal bearing capacity. And D is the nominal diameter of the bolt, which is 20 mm, and T is the minimum thickness of the members. So there are gusset plate and there is a single angle member, and the thickness of angle is 6 mm and the gusset plate is 12 mm. So the minimum value of the T will be 6 mm. And we know the value of the ultimate strength of the plate is 410 Newton per mm square. So basically we will be substituting in this equation of VNPB, in which 2.5 KB is 0.505, and we'll be getting an answer of 62,361, and its value is in Newton. Now we have to find the design bearing capacity, and this is also given code as VNPP divided by gamma NP. So we'll be substituting the value of gamma N, which is 1.25, and getting 49.86. So the value for the design strength of the bolt will be the minimum value based on VDSP and VDPB. So this will be 45.27. Now the design of connection basically means to finding the number of bolts. So the number of bolt will be equal to the factor load divided by the design strength of a single bolt. The factor load we already calculated as 75 kilonewton divided by the bolt value, or this design strength of bolt is 45.27. 1.65 will be obtained. So we assume two numbers. Now we'll check for the design compressive strength PD value for the angle section. Now the design compressive strength is given in clause 7.1, and it is given as PD is equal to AE into FCD, where A is effective sectional area and FC is design compressive stress. Now this is how we provide the connection, the two bolts. This is 50 the pitch, this is 35 the end distance, and this is how the load will be acting. Now in clause 7.1.2, under the design of compression members in page 34, the design compressive stress is given by an equation, and this equation is given as Fi by gamma m0 divided by phi plus phi square minus lambda square the whole raised to 0.5. So we had to first calculate the effective slenderness ratio. Now for single angle section, the effective slenderness ratio has to be taken from clause 7.5.1.2, which is in page number 48. So when we go to page number 48, we can see the effective slenderness ratio for a single angle strut which is connected through one leg. So here the you can see this angle section is connected only through one leg, so the slenderness ratio has to be considered in a different way. So the equation of effective slenderness ratio is given under this clause 7.5.1.2, and is root of k1 plus k2 lambda vv square plus k3 plus lambda phi square. Now the value of k1, k2, k3 are the constants depending upon the end condition. Now we have designed for two bolts, and we assume that two bolts will create a fixed kind of support. Now go to table 12 of page number 48, and we can see a table in which, based on the number of bolts, we can take the value of k1, k2 and k3. Now we have two number of bolts, which means it is greater than or equal to 2, and correspondingly the k1 value is 0.2 for fixed condition, 0.35 is the k2 value for fixed condition, and k3 value will be 20. Okay, now we will go back to our slenderness equation, and we have to calculate the value of lambda vv. So lambda vv is equation is given as L divided by RVV the whole divided by epsilon into root of pi square into capital ER. So this is capital E, which is modulus of velocity. There is also a small printing mistake. So this is actually capital E divided by 250. Now we have to find the value of this value. This is also given in the explanation for the equation, in which this is the yield stress ratio, which is 250 by the whole raised to 0.5, and the yield strength of the material we assumed is also 250, so this will be cancelling and this value will be 1. L is the unsupported length, center or the unsupported length. RVV is the value that we obtained from IS 808 for the 90 by 90 by 6, and it is 17.5 mm. And E is the modulus of velocity of the steel, which is 2 in 10 raised to 5, and epsilon value is 1. When we substitute all this value, we will be obtaining lambda vv as 1.929. Now another value which is required to calculating the effective slenderness ratio is lambda phi. Now this is given as, equation is given as b1 plus b2 divided by 2t the whole divided by the earlier thing. Now b1 and b2 is given as the width of the two legs, and t is the thickness of the leg. Now we know we are using which angle section, 90 by 90 by 6. So 90 by, we are using an angle section of 90 by 90 by 6 angle section, which means one of the leg size will be 90, the other size will be also be 90. So the b1 and b2's values are, here it is 90 only, it is both are 90, and the thickness is 6 mm. So I'll be substituting this value over here to calculate lambda phi value. So b1 is 90, b2 is 90, because we are using an equal angle section. So this is what an equal angle section means. It is 90 by 90 by, and the thickness is 6. Okay, so b1 is 90, b2 is also 90. So I'll be substituting the value, and I'll be getting a value of lambda phi as 0.1688. Now we'll be substituting all this value in our effective slenderness ratio. So there is the lambda vv value, lambda phi value, and also the k1, k2 and k3 values. So everything is given in under the clause 7.5.1.2 in page number 48. So 0.2 everything will be substituted, and I will obtain the value of the effective slenderness ratio as 1.439. So this is a value obtained. Now what we have to do? Now we have to go back to our clause, which is talking about the design compressive stress, which is 7.1.2.1, and here once we are getting lambda, we can calculate the value of phi. The phi, where phi is 0.5 times 1 plus alpha into lambda minus 0.2, is actually lambda minus 0.2 plus lambda square. So here the lambda will be the effective slenderness ratio for an angle section, and the alpha value, it is the imperfection factor, and this is given in table 7 of page number 35. And we are selecting an angle section, and which means it belongs to class C, and the value of imperfection factor alpha will be 0.49. So this will be obtained from table 7. So we'll be substituting the value of lambda e and alpha, and solving, we'll get the value of phi as 1.839. Now we have obtained every values possible in the general equation of FCD, which is given in page number 34. Now this equation was Fy divided by gamma m0 the whole divided by phi plus phi square minus lambda square whole square. Now we will be substituting. The Fy is the yield strength of the material which we are using as the compression member, which is 250. Gamma m0 is obtained as 1.1 from table 5, and the remaining values we will substitute. We are getting a design compressive stress as 76.168. Now we have to find the total design compressive strength PD, which is given in clause 7.1.2. This will be the effective area, and this is the area of the 90 by 90 by 6 member, and this area will be obtained as 10.5 centimeter square, which is 1050 only. This we have written earlier, multiplied by this design compressive strength, we will be obtaining a value of 79,934, which is basically 80 kilonewton. Now what was our factored load? It was 75 kilonewton. So this value, which design compressive strength for the angle section we assumed, which is 90 by 90 by 6, is greater than 75, that is 80 kilonewton. That means our section will be safe